Yeah, I can. All right. Thank you for the invitation, and thank you, Manita and Jim, for organizing this wonderful conference. And today I'm going to talk about a few new ideas and new results on how to explore large-scale climate dynamics through physics of complex systems. I'm going to start with the proposal of a causal inference method for climate fields, and then on a first application of such method to better understand the pattern effect. Can you hear me? I can. Okay. All right. This work is part of a very long-term and general goal of developing a comprehensive framework to study and understand the main causal mechanisms governing large-scale climate dynamics, first, and second, the response of such mechanisms to forcing, whether natural or anthropogenic. And as many of you know, this is a great challenge of today's science, mainly because the climate system is a complex system, meaning that it is composed by many subsystems, such as the hydrosphere, atmosphere, and so on and so forth, and their interactions. And crucially, these interactions vary across a vast range of spatial and temporal scales. Just as an example of how highly non-trivial it can be the change of regional climate variability to external forcing, this comes from a very long simulation of the IPSL Earth system model of the mid to late Holocene, where what I'm showing you is the first principal component of the sea surface temperature in the Indian Ocean, and showing you that 6,000 years ago, at least in this model, the variability was dominated by El Niño-like variability. And because of slow changes in the Earth's orbit, which caused changes in the whole Indo-Pacific region, this mode gradually disappeared in favor of the Indian Ocean basin mode that we observe today. So studying and understanding such a system and its response to external forcing is extremely non-trivial, but is an important problem both in the natural and mathematical sciences. A useful framework to tackle such a problem is probably not to focus on very high dimensional spatiotemporal fields, meaning on all the details in these fields, because it's difficult to interpret and to study, but to focus on spatiotemporal patterns and their linkages, which emerge out of the variability of this high dimensional spatiotemporal field, first. And second, trying to understand how these modes and their links may change in external forcing or change in the past. Now, if you accept this way of looking at the system, there are already two main problems. The first one is how do we identify components of the system? And the second one is how do we infer the linkages among these components? Now, the very traditional way to do so is through either climate indices or EOFs. And here I'm going to focus on indices just because of time constraints, where climate indices are simply time series averaged over a certain regions that we may care about. And crucially, this process is not automated. You have to choose what are these regions. And we focus always on very few modes at a time. So this brings us to two main issues. This framework is not a comprehensive method. And second, the indices that we're choosing in the current climate may actually be not that relevant in past climate, in future climates, or across models. And third, when we're trying to understand how these indices are linked to each other, we use correlation analysis, at least traditionally. So this brings us to the proposal of a simple framework for dimensionality reduction and causal inference in spatiotemporal fields. And here I'm going to focus on kind of a high-level description without getting into the many technicalities. In order to show you the framework, I'm going to focus on the sea surface temperature field, monthly anomalies after removing the seasonal cycle. And I'm going to focus on a very long 300 years run of the GFDL CM4 model, by control meaning that the CO2 is kept stationary at pre-industrial level. So this is a stationary system. And as a first step, we're going to reduce the dimensionality of this field in a set of patterns. And these patterns are defined first as sets of time series that have large average pairwise correlation. So these are kind of proxy for modes. All these time series go up and down altogether. These patterns are regionally constrained, so they're bounded to live in some regions. And so they're proxies for climate indices. Now the whole field is decomposed in a set of patterns. So all modes and variability and their interaction can be studied simultaneously. Now for each one of these patterns, we can identify a time series by computing, in this case, the integrated anomaly of all the time series inside. And crucially, this pattern, as I told you before, are regionally constrained. So this allows us to answer this question. How is local climate variability in some regions affecting the variability everywhere else? Yeah. There is an algorithm behind that I'm skipping over just because of time and because of not going into technicalities. But it's a community detection algorithm that has to be set carefully, and we can talk about it later in Q&A or in discussion. In order to understand how these regions are linked to each other, given their variability, we use methodologies from causal inference. Now, the most important thing to remember about this causal inference part is that, as Valerio showed yesterday, it has been noted in the last 10 years, more or less, that there is a strong parallelism between interventional causality and linear response theory in statistical physics. This is true both for the simple case of smooth responses using fluctuation dissipation theorem, but it's true, but especially true also for the more general tools like the one that Valerio showed yesterday using linear response theory a la well. Now, I'm going to focus on the very simple case on fluctuation dissipation, and we're going to start a discussion from a physical definition of causality based on external intervention as given by the group of Vulpiani in 2020. We start from a dynamical system that is n-dimensional, for which we have observations that come in terms of time series. And then we say that a variable xj causes xk if a perturbation at variable xj at time 0 will cause, on average, will induce, on average, a change in variable xk at time t. This connects the idea of causality to what we do usually in physical experiments. We perturb fluid flow somewhere, and we're trying to see how this perturbation evolves in the system. Now, if you accept this physical definition of causality, then you would realize that there has been a lot of work in the last 60 years or so in the statistical physical community to answer this very question. And in its simplest formulation, it boils down to the fluctuation dissipation relation. Now, skipping all the details, the main object of the fluctuation dissipation relation is what we call response function that gives us the average in terms of ensemble average of changes in a variable xk at time t, given an infinitesimally small perturbation of a variable xj at time 0. Now, this part is proper of non-equilibrium statistical mechanics because we have perturbed the system and now it's changing. And the magic of fluctuation dissipation theorem is to relate it to this part on the right, where all the variables here are defined in the unperturbed system, where this is just the variable xk, these are ensemble averages, and this is the gradients of the invariant measure of the system, or the stationary probability distribution, if you prefer. Now, what is this stationary probability distribution? Usually, especially in high-dimensional system, we have no idea. So we are going to make a very crude assumption, probably illegal in many countries, which is considering the case of linear systems, for which that rho is actually a Gaussian, and for which we can solve that formula analytically. And for linear system, we recover this very simple formula, which is that the response after perturbations can actually be written as a suitable combination of covariance functions in the unperturbed system. And the links from now on of xj, of a variable xj at time 0 to xk at time tau is just given by this response matrix. Okay. So again, we started from a high-dimensional system. We used some methodology from community detection that I didn't go into details to partition the whole field into patterns. To each one of these patterns, we assign a time series that gives us its average variability. We computed the responses, and now I'm going to extract two variables out of these responses. One of them is El Niño, and the other one is tropical Atlantic. Now, here on the x-axis, you have time. On the y-axis, you have these responses, normalized in this case. And I remind you, ENSO causing tropical Atlantic in this framework means that the tropical Atlantic will respond to sea surface temperature perturbations in ENSO. It will respond to perturbation in ENSO. Now, without going into details, at least the short time scales, there has been lots of work to understanding such links using models, and that's why we use this field. But if you look at long time scales, then you start seeing some results that we do not know what it is. It doesn't go to zero, this perturbation, this response. The first one looks like noise, but the second one, it doesn't really look like noise, and in fact, it's more or less of the same magnitude of the response for short time scales. And this brought us to one of the main issues for real-world data, which, surprisingly enough, has not been taken care very seriously in the literature, as far as I know, which is that whenever we use fluctuation dissipation relation for a time series, we actually always have spurious results for two reasons. The first one is the simple one, sample size, it's finite. And the second one is more complicated. We have non-IID processes, and so we have large autocorrelations that will result in spurious results. I will skip over a few months of work, but what we proposed is as the first, as far as I know, analytical null model for the fluctuation dissipation relation, such that if you have a response matrix and you actually want to look at if you have the response matrix for each couple of variables, xk and xj, you automatically have the confidence bounds of the fluctuation dissipation formulas given by this normal distribution. And this normal distribution is parametrized by the length of the time series, the lag1 autocorrelation, phi k and phi j, and their variances. If the length of the time series is infinite, then there is absolute confidence, and these confidence bounds go to zero. If it's finite, it will depend on the length of the time series, lag1 autocorrelation, and variances with this formula. And here is an example for the responses I showed you before, focusing on the plus minus 3 sigma of these confidence bounds, where you can see that actually the only one that are statistically significant are the one at short time scales. And even this kind of response that seems kind of, an order, it doesn't seem really like noise. It actually comes just from the autocorrelation of the time series themselves. Okay, so again, we started from a high-dimensional system. We reduced its dimensionality. We computed response matrices in this low-dimensional system. And now I showed you an example of these responses and confidence bounds. One thing that is left to do is to look at metrics. We're going to focus on two metrics. The first one is what we call cumulative degree of causation, which is just a very fancy way of saying just cumulative responses. Once you choose a variable j, you can look at the cumulative responses at the whole world to infinitesimally small perturbation at this region, just as by looking at the cumulative response. This is for El Niño, but then you can switch to any region of interest, from the Indian Ocean to the South Tropical Atlantic to the North Tropical Atlantic. And finally, if you consider each one of these regions, you can think of computing summing up in absolute value all these terms and obtain a value of what we call strength, meaning that large values of this strength will imply that this region, for example, is able to influence a large portion of the climate network we're studying. We're focusing on interannual variability here, and it's not surprising that the ENSO is the one that pops up. So for the first part of this talk, let me give you a summary. The main point is to start from a high-dimensional spatio-temporal field, difficult to interpret and study, and then have come up with a simplified description of the data based on dimensionality reduction and causal inference, which allows you to have a qualitative understanding of the system. It allows you to have attribution, to study attribution, causal mechanisms, response to forcing, and model evaluation. Now here I'm going to show you a first application of such framework for what is the pattern effect. And here a disclaimer, the main expert in the pattern effect is Ming Zhao from GFDL. So before explaining what is the pattern effect, I have to explain what is it. Consider an input of CO2 in the system, like is happening right now. So if we have more trace gases inputting in the atmosphere, as all of you know, this will create a global energy surplus because there is less terrestrial radiation that is escaping the Earth. And the climate system will want to go back to energy balance. In order to do so, it will warm up. And as I told you before, this is a very complex system. So this original warming will actually cause changes in the system. For example, the spatial coverage of snow and ice will decrease, cloud properties will change, and so on and so forth. And this will generate positive feedbacks on temperature or negative feedbacks on temperature, meaning that each one of these processes will end up amplifying the original temperature change or dampening the original temperature change. And there has been an old assumption, which is that the global mean radiative feedback depends on global mean temperature changes. But actually in the last 10 years or so, it has been recognized that patterns of warming at the surface actually matters because they can cause different responses in the climate system. This means that given the same global mean change in temperature, if you warm up, for example, the Eastern Pacific more than the Western Pacific, then this can result in different feedbacks and then in different pattern effects. Okay, so what people care about here is in this field is how do changes in patterns of warming actually drive changes in radiative feedback, in net radiative flux at the top of the atmosphere. In order to do so, the state-of-the-art way to look at this problem is through Green's function model intercomparison protocol, which it works as follows. You have an atmospheric model, which is forced by boundary condition, which is sea surface temperature and sea ice concentration. Let's focus on sea surface temperature here. And you run first a control run. You remove a transient, and then you take the average of any scalar of interest in the atmosphere. Let's say that, for example, one of the scalar of interest can be the net radiative flux at the top of the atmosphere. And then, as a second step, you run patch simulations, meaning that you come up with some patches and you independently apply a step function, let's say +1 Kelvin in sea surface temperature for T greater than 0. And you run the model again forward in time. And you look at the difference between the scalar of interest you were looking at before, everywhere in the atmosphere, and the new run, before the pi control and in the new run that is forced. And then you can save this delta F. The main point is that, glossing over many details, but the main point is that by knowing the patches of where you apply the perturbation, by knowing the strength of the perturbation, and by knowing the change, delta F, you can come up with some sort of Jacobian that relates changes in sea surface temperature with changes in any scalar of interest in the atmosphere, at least for this model. And in order to study relationship between patterns of warming and radiative flux, that is it. However, you still want to actually understand if this thing has any skills. And in order to do so, you basically consider the change in SST in a forced run, for example, 1% CO2 run, 4 times CO2, or in this case, historical changes. And you're trying to see if you can recreate simply from sea surface temperature changes, the global mean values of the net radiative flux at the top of the atmosphere in this new run. Now, this way of looking at the system has few positive things, but there's also some issues, and I'm going to focus on the issues here. First of all, it requires a couple hundred simulations, so it's pretty expensive computation. Second, and most importantly, physically, the ocean here is just a boundary condition. So there is no real coupling. The ocean can affect the atmosphere, but the atmosphere cannot affect the ocean, and the ocean cannot affect itself if you put a perturbation. So there is also no teleconnections, and then it requires relatively large perturbations. And we can talk about this step because it's an important one if there is time later. So this brings us to a way to try at least to solve those problems. We're going to focus on two variables, sea surface temperature and net radiative flux at the top of the atmosphere, that from now on I will just refer as TOR. We consider monthly anomalies, so we remove the seasonal cycle. And here again, we consider 600 years of the GFDL CM4 run. So stationary climate with pre-industrial CO2 run for 600 years. Importantly, we remove low frequency variability. And again, ask me later if you're interested why, because there is not too much time. As a second step, we can reduce the dimensionality of the system. Here, we can use the community detection tool that I showed you before, but you can use EOFs and you can use whatever you want, actually. For each pattern here, we're going to have two time series, one for sea surface temperature and TOR. And importantly, we can define at each instant in time a state vector. We can define a state vector such that at each instant in time is encoded by 2 times n numbers that give you the state of the system at that time. Why n? Because that's the number of pattern. Why 2? Because we have two variables. And then we use this, we compute this response operator. You have to believe me here, the linearity assumption is still okay for this application. And we compute confidence bounds so that we know what is spurious and what is not spurious. And then all the causal links between sea surface temperature and net radiative flux at the top of the atmosphere are basically hidden in this operator, and then we can use different formulas as I will show you in a second on how to reconstruct them. Now, if this works, it comes with some benefits. First of all, it requires only one simulation, which climate models already have. Every climate model have a PyControl run that is sitting somewhere in some server. Then, now we are looking at the coupled system. So the ocean affects the atmosphere, but the atmosphere affects the ocean, and the ocean can affect itself too. We can capture the role of teleconnection, which are going to be important in longer time scales, and these are not captured in Green's function protocols at the moment. And we can focus on very small perturbation. Actually, this is only true for small perturbation. Now, you may ask if I lost my mind of using these linearity assumptions and so on and so forth. So we're going to look at the skills of this operator. As I told you before, the operator is inferred in a PyControl run with pre-industrial CO2. Now we're going to consider a forcing field, which is the sea surface temperature field, in two runs, the 1% CO2 run and 4 times CO2 run. 1% CO2 run just means that you start at time 0 with pre-industrial CO2 concentration, and at every year, you add plus 1% for 150 years. After 140 years, you reach quadrupling of CO2, but it's an incremental change. In the second one, we have a step function of plus 4 times CO2 concentration, and so it's a very abrupt, non-linear change in the system. And the question is, if I give you the sea surface temperature field in these two runs, and I convolve it with the linear response operator, we should be able to reconstruct, to have a prediction of an ensemble mean change for the radiative flux at the top of the atmosphere. Now, what you see on the left is the prediction of the theory for 1% CO2 run, and on the right is 4 times CO2 run. Focus on the left first, where on the x-axis you have year from 0 to 150, and here you have the change in watt per square meter. In blue, you have what the climate model actually simulates, and in black you see what the linear response theory using fluctuation dissipation would actually reconstruct. And you can see that if you think that this is what this gives you is a reconstruction of the ensemble mean, and so it seems to be pretty good. On the right, you start seeing the failure of the theory, which happens when you have a very strong nonlinear change that may happen when you have 4 times CO2. And here, basically, I would still argue that it captures kind of a general curve, but we are off about 2 or 3 watt per meter square. And this is if you use EOFs, which actually, for this dimensionality reduction, we actually have a worse reconstruction. There is work on understanding, explaining why that should be the case, and we're actually working on that. But this is just to show you that for the next results, you should put more weight on the results coming from the community detection rather than EOF. Now remember, we didn't start these in order to trying to understand if an operator has some skills or not. What we try to do actually is trying to understand what is the relationship between sea surface temperature warming patterns and changes in radiative flux at the top of the atmosphere. One first order way to do so, it may not be the best, but is what has been done in the literature so that we can compare with them, is what is called sensitivity map. Meaning that in these maps, in each grid point, we are plotting the change in global mean radiative flux at the top of the atmosphere if we force with +1 Kelvin in sea surface temperature in that point. So this map relates local changes in sea surface temperature to global mean changes in radiative flux. This is for the EOF and this is for the pattern effect. Sorry, this is for the community detection. The formulas to compute these changes come from this, where here you can see the integral, the upper bound is just infinity, time goes to infinity. And here what I'm doing is to focus on the shortest time scales of 1 month. And I do this not because it's correct, but because I want to compare with results in the Green's function protocol. Then I'm going to show you longer time scale in a second, and in 2 minutes I'm done. So, at shortest time scales, these results are actually consistent with what is obtained by the Green's function protocol. So by actively perturbing the system. You have to believe me on this. And this means that if the system is not coupled, it seems that 1 month more or less seems large enough for the atmosphere to capture these perturbations in sea surface temperature. And the main feature that you should see here that is important in the literature, and that is what is known now as the pattern effect, is that there is this dipole of sensitivity with positive sensitivity in the Eastern Indian Ocean, in the Eastern Pacific, and positive and negative sensitivity in the whirlpool. And there is no clear, qualitatively they are very similar, the EOFs and the community detection. They tell the same story, even if they are using a very different algorithm actually to compute these patterns. Now, as soon as you start looking at longer timescales, you see that this feature of this dipole in the Pacific actually disappears. And the whole Pacific now shows a negative sensitivity to positive perturbation in sea surface temperature, and this is true for both methodologies. And after 3 or 4 years, this converges, okay? And this is what I can show you after 10 years. Again, this is dimensionality reduction with using EOFs. This is community detection. Put some weight more on the community detection one. Where the main point here is that there are some differences, but the main point is that the main negative sensitivities comes on average from the tropics, meaning that if the tropics, meaning that for the same global mean temperature change, if the tropics warm up more than the higher latitudes, the system is more able to cool itself by radiative cooling. That's the main interpretation. While if you keep warming the high latitudes, on average, depending where here, you actually have a positive feedback. So it's more difficult for the system to radiative cool itself. Okay, so let me go to conclusion. I show you first a proposal of a data-driven framework for dimensionality reduction and causal inference in climate fields. I hope by convening, as Valerio was doing yesterday, that this is a powerful tool. It depends on many details, so it may be sometimes applied. It can be applied for certain systems and not to others, so there is a lot of thinking, especially in the pre-processing when you're doing these things. But it allows also to reconstruct variables given notions of other variables with implications for paleoclimate reconstructions too, maybe. Allows us to propose a protocol to diagnose and understand the pattern effect. And what I showed in the end is a preliminary result. It shows that main sensitivity of changes in the radiative feedbacks come from the tropical Pacific region, all of it. different from current understanding where there is a dipole in this region. And actually, on average, negative sensitivity is in the tropics and higher, and positive sensitivity is more on average again in the higher latitudes. That's it. Thank you very much.
Okay, thank you very much for the talk. The questions. I would like first to invite the students to ask questions, if they like. There's one.
So yeah, it's a very nice and interesting talk. So I just want to understand, like, is this sort of a study is good to have like multi-model or the multi-ensemble from the single model?
It's a good question, and what I can tell you right now is that I would like to try both. Because for what I see in the literature, the multi-ensemble mean actually is much more similar to observation than how is single models. So maybe by looking at multi-ensemble mean, it allows us to go closer to the real world and not stay in the model world like I've been doing here. But it's still interesting to look at how different models reproduce this pattern effect, because the climate sensitivity of the system is actually influenced by this pattern effect too. And we have a huge divergence in climate sensitivity in climate models. And it's an open question, how does this depend also on the pattern, on how the patterns of sea surface temperature are actually changing.
And just one more follow-up question, like, how do you control the magnitude of internal variabilities if you are going to use a multi-model approach? Because the internal variabilities are very different in all the models, right?
I don't have an answer for that. Like, it's a difficult answer. It's something to think about. Yeah.
There are more students' questions? From the back row? No? Okay. You're not a student, right? But it's okay.
Doesn't work. Oh, okay, thank you for your talk. What is the definition of the top of the atmosphere? What you're using here? It's because it's like a box model, or it's really unclear, and especially because how to measure radiation at the top of the atmosphere.
It's not a box model. It's a fully coupled climate model. Here, like top of the atmosphere, just the last layer of the atmospheric model.
Here, what do you mean, like a last layer?
I don't know how up it goes, actually. Yeah.
Okay, are there further questions from the audience? I have one. Oh, there's one from David over there.
Can you project the modes of variability that you find back onto the ones that are sort of commonly used in the community, the NAO and so forth? Yeah?
Project, you mean in a qualitative way? Like,
well, I'll just relate them. I mean, there's this whole similar...
I think so. Like, especially in... what is it? For example, let's say that if you take the first principal component of the system, let me give you the one that I was showing you before. This is much better. If you take the first principal component of the sea surface temperature, it will actually correspond to the one that has the largest causal strength. Sorry, I have to go back there. Okay, so if you take the kind of the time series that comes out of this, as basically a 99%, a 0.99 correlation with the first PC in sea surface temperature. Once you go after the first mode, then that is where the problem starts, because what is being used in traditional climate analysis is EOFs, but EOFs have also problems. EOFs are orthogonal to each other. And so now, because of that orthogonality constraint, it's not clear how much after the first mode these modes are physical or not, because they have to respect this orthogonality constraint. So we can do it qualitatively. For example, what you have here, if you zoom in the Indian Ocean and you look at the first principal component, then you have an Indian Ocean basin mode. And it will be very correlated to what you find here, to the time series that you find here. So there is a relation between the two, yeah.
So, and I don't know if it's a really related question, a sort of different question, but you can do EOS of sea surface temperature, but you could also do an EOF of, say, Laplacian of sea surface temperature or something like that, and you'll get different modes, right? The first mode might be different, right? Is that useful? I mean, to just take the same data set and, look at the Laplacian or the gradient or something like that?
There is no clear answer there. The only thing I can tell you there is that once you design these things, you shouldn't think about these as like one ultimate answer that there is no improvement that you can do later. The most important problem in these sorts of analysis is actually not the mathematical part or the physical part, but it's actually to choose the proper variables that you care about for the process that you want to understand. So that will always change depending on what you want to understand. And we look at just the surface temperature in this case, just because it relates to old work that has been done by Cécile Penland in 89 and 95, showing that at first order, by looking at the surface temperature, you can approximate it with linear Markov models. But depending on what is the problem you're interested in, you can use multivariate, or you can choose different fields, and it depends on the specific question you're asking.
I have a question. In the old days, we were not supposed to do EOFs in particular, and of the SST in the Pacific, because there's an oscillation, right? And as you said, EOFs are orthogonal to each other. If there's an oscillation, there are artifacts, and you should not do this. So, and we were supposed to do POPs, right? Principal oscillation pattern analysis, based on the lag-1 covariance metrics, which you're also using, right? So what happened to the POPs?
It's just a different way to look at the problem. Like here, basically, I'm related more to the concept that we still use in climate science of looking at regions and trying to connect different regions to each other using that. Actually, it's something that is really closely related to the POPs, right? The CT is 0 minus 1. It's just a different way to look at the problem.
But POPs are out of fashion now. POPs are out of fashion. Which is sad. Okay, one final quick question. Then I have one more comment, actually. You also said this, actually. SST is not the boundary condition for the atmosphere, right? It's the heat flux, basically. So the ocean plays a role.
In the Green's function protocol, is what I was saying, right?
Yeah, but also in yours, right?
Yeah,
Using SST.
Yeah, I want to make a difference there. In the Green's function protocol is a boundary condition, meaning that if you perturb it in one place with one step function perturbation, it will not change everywhere else, right? That step function will stay there because everything else is described as before. But here it will change, right? If you put a perturbation here, whether it's with EOFs or this community detection methodology, this will impact the atmosphere, but it will also impact everything else in the surface temperature, because it's inferred from a coupled run.
You could also use some other temperature and some other level.
Oh, yeah. I mean, what I have in mind when I do this is to use all variables, right? And then here is the simplest first order understanding.